Unit 5B, Lesson 3. In this lesson, we're going to begin by discussing the difference between prisms and pyramids, and then after that, we're going to solve some equations based on information given to us with three-dimensional shapes. First thing we're going to discuss is some key features of prisms. So if we're talking about a prism, they have two identical ends, which we refer to as the base. In this case, those bases, the ends, are going to be triangles. In this other one, those bases are hexagons. Another feature is they have all flat sides, which we can see. In this case, contains rectangles. In this case, again, containing rectangles. They have the same cross section all along its length. So if I would slice anywhere along the length of this triangular prism, they would have the same cross section, that same surface. Same with this hexagon. If I would slice along anywhere along this hexagonal prism, that surface is going to be a hexagon. And then the shape of the ends give the name of the prism. In this case, our bases are triangles, so this would be a triangular prism. In this case, the ends, the bases, were hexagons, so this would be a hexagonal prism. Now we're going to discuss pyramids. A pyramid, the basic definition of polyhedron that has a polygon for a base, and the lateral faces are triangles. So in this case, the base appears to be a square. It could be a triangle or some other polygon. And then the faces all have to be triangles, which you can see, and they meet at a point, a vertex. Some key parts we would use or try to identify in a pyramid is the height and the slant height. We can find those pieces of information because we have a right triangle that is created here. So if we're looking for one of those lengths and we have the other, we could use the Pythagorean theorem, as well as if we had this length. So difference between a prism and a pyramid. A pyramid is going to meet at one vertex. A prism is going to have two bases that are identical shapes. Next, we're going to discuss the relationship between different types of lines. If we're giving a three-dimensional shape, in this case, whether it's a cube or a rectangular prism, these ideas are going to apply. So going to discuss parallel lines, skew lines, perpendicular lines, and parallel planes. So first, parallel lines, two lines that are coplanar, meaning they lie on the same plane and do not intersect. So we'd have many examples that work in this case, but if we extend line DC, that would be parallel to line AB because they lie on the same plane and they will never intersect. Skew lines, two lines that are not coplanar and do not intersect. So in this case, we could use AB. Line AB is going to be a skew line compared to line CG. They are not on the same plane and they will never intersect. Perpendicular lines, two lines that intersect to form a right angle. Again, many examples. We could use line CB and line CG. They intersect to form this right angle. And then parallel planes, two planes that do not intersect. So remember, a plane is like a flat surface that extends in all directions. So if we had plane ABCD, that would be parallel to plane EFGH. They are never going to intersect if we extend those planes in all directions. In our first example, we want to use the rectangular prism to identify the following: parallel segments, perpendicular segments, skew segments, and then parallel planes. There's going to be many different possibilities we could list for these examples. We're just going to list one for the sake of time. So first, parallel segments. If I'm looking at plane ADHE, this side of the rectangular prism, I know AD is going to be parallel to EH. They're coplanar and they will never intersect, so AD is parallel to EH. We're briefly going to talk about notation when writing these statements. Remember, these two lines indicate that the two segments are parallel, and I am just going to have a line segment above to indicate this is a segment rather than a line. If we were referring to two parallel lines, for instance, if EH extended in both directions and AD extended in both directions, then our notation would be a line with two arrows above it, indicating that it's a line going in both directions. If you do not see these arrows going in both directions, that indicates it's a segment, which is why I did not include the arrows in this example. Next, we want to identify perpendicular segments. Again, there would be many different possibilities we could use. We're just going to list one example. Suppose I was referring to segment CD. I know that is going to be perpendicular to segment CG because they intersect to form a right angle because this is a rectangular prism. Again, a little talk about notation. If you see the upside down T, that means perpendicular. I did not include arrows above because we're referring to segments and not lines. Next, we want to identify two skew segments. Remember, skew segments are going to be two segments that never intersect, but they are not coplanar. They do not lie on the same plane. So, in this example, I could use segment EH, and that is going to be skew to segment AB. These two segments are never going to intersect. If they extended those lines, they would never intersect, and they are not coplanar. Notation in this case, there's no special symbol we can use to indicate whether two segments or two lines are skew. So we just have to say segment EH and segment AB are skew. The last thing we want to identify are parallel planes. Just like the rest of these, there's many different examples we could use. Suppose I was referring to plane ABCD, the bottom portion of this rectangular prism. That would be parallel to plane EFGH. If we extended those planes in all directions, they would never intersect. So notation, how we write this, we're just going to say ABCD, indicating that plane is parallel to EFGH. In the next example, we're going to use some algebra to solve for the variables x and y. So a parallelepiped is a prism where each of the faces is a parallelogram. So we want to find the value of x and y in the following parallelepiped. So first we're going to solve for the value of x. So since this is a parallelepiped, meaning each face is a parallelogram, I know that if this length is 15, that this other length must be 15 as well, because that's the definition of a parallelogram. Opposite sides are going to be congruent. So if this length is 15, it must be congruent to this length, which is 2x plus 3. So we can create a linear equation. 2x plus 3 must be equal to 15. We would subtract 3 to the other side to get 2x equal to 12, and then divide by 2, we get x is equal to 6. Now we want to solve for the value of y using the same basic idea. If this length is 3y minus 1, since this is a parallelogram, it must be congruent to y plus 7. So we set up a linear equation, 3y minus 1 equal to y plus 7. Get like terms on the same side, so we could add 1 to this side and subtract y to this side, leaving us with 2y equal to 8. Last step, divide by 2. We get y is equal to 4. So using definition ideas we talked about with parallelograms previously. Now we're on to the last example. A straw is placed into a rectangular box that is 3 inches by 4 inches by 8 inches, as shown in the diagram. If the straw fits exactly into the box diagonally from the bottom left front corner to the top right back corner, how long is the straw to the nearest tenth of an inch? So in order to solve for the length of the straw, we have to picture a right triangle contained within this rectangular prism. We have one leg, another leg, which is the height of the box, and then the diagonal going from one vertex to the other, which represents the length of the straw. We know what this length is. It's 8 units. We're trying to find this length, which is the straw. We'll just use L instead of S because my S's look like 5s. So we're trying to find that length. We need to find this value because right now we have one unknown and a second unknown value. But if we imagine this triangle, since this is a rectangular prism, we know this is a right angle as well. So we can use the Pythagorean theorem. 3 squared plus 4 squared is going to be equal to, let's just call this value c, is going to be equal to c squared. So now we just go through, simplify. 3 squared is 9, 4 squared is 16, 9 plus 16, we get 25 equal to c squared. Now we would take the square root of each side. We would get a positive and negative answer, but we're only going to take the positive because we're talking about distance. So we get c is equal to 5 units. So now if we substitute that value of 5 in, now again we're going to use the Pythagorean theorem. We have a right triangle. We know the value of both legs. So we can set up 5 squared plus 8 squared is going to be equal to L squared. 5 squared is 25. 8 squared is 64. So if we take 64 plus 25, that's going to be equal to 89, is equal to L squared. Now to get L by itself, we take the square root. And in this case, we're going to get a decimal. So if we plug this into our calculators and round to the nearest tenth of an inch, we would get L is approximately 9.4 inches. So really, this problem didn't involve any complicated math. It's more visualizing, recognizing that you have to apply the Pythagorean theorem twice. So in this lesson, we discussed the difference between prisms and pyramids. We also discussed parallel, perpendicular, and skew segments and lines, as well as parallel planes. And then we finished using basic ideas of parallelograms and rectangular prisms to solve a few algebraic expressions.